Okay, so everything I'm going to talk about or most of it, what I'm going to talk about is joint work with my student Marcin Kotowski, who is here, and he's not to be confused with Michal Kotowski, who is identical.
Not anymore.
As a twin, but they're both excellent students so far, I am sort of a. It's a pleasure to be here in beautiful Paris, where everything is pretty, the weather and people are well dressed. I almost put on a bow tie this morning. I'm a guest here as a probabilist, and one of the things that come up in probability as a theme is what is really lucky and what is not lucky. So there is a lot of randomness, and some of it you can characterize as luck and some of it not. So for example, if you win the lottery, that you can say that you're lucky, but if you don't win the lottery, then it's hard to say that you're unlucky. That's kind of the law, right? You just play and you don't win. And then there are sort of other things like parking tickets. For some people, if they get a parking ticket, they say that it's unlucky. But for me, it's just kind of a law that I usually try to pay, but then I think about math and I forget, and I get a parking ticket, and generally you get 3 or 4 in a year, and it becomes kind of part of life, and you accept it, and so on. So a little bit of randomness can change the system in a way that you may not like. And so this is the theme that I want to start with, and it's a theme of what's called the Anderson model, or random Schrödinger operator. So it's in the world of eigenvalues. So the Anderson model for random Schrödinger operators were introduced by Anderson, who is a math physicist in, I think, 52. It's a very, very simple thing. So let me tell you the one-dimensional version. Okay, so you consider the standard Cayley graph of Z, right? Which is just if you write its adjacency matrix A, then it looks like you just have the ones on the off diagonal and then zeros, right? This is this very well. So it's a kind of infinite by infinite matrix. And if you want to look at what the eigenvalues are of this infinite by infinite matrix, well, you try to solve the eigenvalue equation, and then you quickly find that the solutions are all just sort of sign things sort of sampled at discrete points. So right away you see that these things cannot be eigenvectors because they don't live in L2, right? I mean, they're periodic or almost periodic or something like that. So certainly. If you try to find eigenvectors of this operator, you find that there are none. Okay, and if you draw, what the eigenvalues look like, eigenvectors, the solutions look like, they're kind of eigenstates that you just sample at discrete points of Z. Now, you can think of this thing as a model of electricity. In some sense, because you think of Z as a long wire, and then you solve, say, the Schrödinger equation to understand how electrons travel, and for that you have to diagonalize the Schrödinger equation, and the fact that there are no eigenvectors means that these things are kind of extended, and this extension is essentially means, there is a lot of math involved here. Essentially means that the electrons can travel really far. So in this model, infinitely thin wires would conduct electricity, and you would be very happy. But you know that this is not true, right? I mean, if you look at the cables up there, they're thick, and especially if they're carry a heavy load, then they have to make them thicker. So one model that people studied is when you replace, you put edge weights, random edge weights on Z. So a simple case is when you put A1 here, A2, A2, A3, A3, and the AI are just, say, IID, so that they're picked from some distribution and come random. And as long as these AI are not deterministic, one thing that you find right away is that instead of having these having no eigenvectors at all, you find a full basis of eigenvectors of L2. Okay, so you get a full basis. So this phenomenon is called Anderson localization, and this is well understood in one dimension.
So what are you saying that with high probability?
Probability 1. You get the full basis of eigenvectors. This is an infinite matrix, and whether this happens in 3 dimensions or not, this is a one-dimensional case, is one of the most important open questions of mathematical physics. The physicists believe that the answer is no, but nobody knows. And it's really interesting that this doesn't matter how much randomness there is. If it's very, very high probability, just 1, and with a small probability something else, it's still going to be localized, and the eigenvectors, they start looking much more like that rather than long waves. So this you can think of. Yeah.
It is not known for any distribution.
No, it's not known for anything. Right. No dimensions. It is known except for 1. So in 2 dimensions, it's not even clear what the answer should be, but nothing is known. Okay. The physicists, they know some, but even in 2 dimensions, they disagree. It's funny. So this is a way to think about why cables have to be thick. Bear with me. Eventually I'm going to get to Lie groups, but it's going to take a while. So now, one way to understand this localization is through the spectral measure. Okay, so let's just recall that if you have this operator and you have a coordinate, so in this case a vertex, let's call this O, then the spectral measure sigma of O is defined through the following equality. If you integrate x to the k d sigma O, so integrate, look at the moments of this measure, then these are equal to the OO entry of the kth power of your operator. Okay. So you can also study this. This is a local version of the spectral measure. You can also define this using spectral theory, but this definition usually works as long as your operator is not too ugly. I mean, here you just have to count paths with weights to compute this. And you see that this thing only depends. I mean, the low moments depend on the neighborhood of this vertex. So what's good about the spectral measure? What's good is that you have the following thing. This spectral measure has an atom somewhere, if and only if there is an eigenvector of this operator that charges the point O, okay, which doesn't vanish there. So this is a simple thing to check using spectral theory, for example. So you can look at the spectral measure and check whether you have something like this. So for example, it is known that the spectral measure here is fully atomic. But when you want to study these spectral measures, usually the first step that you try to do is to understand the expectation. Okay, so the expected spectral measure is, it's just a measure and you average over all the randomness. Is sometimes called the integrated density of states in physics, its regularity is usually useful in studying this previous quantity, and it is known in this case that this thing is not atomic in one dimensional. There are no atoms at all. It can be some fractal measure, or it could be absolutely continuous, but it contains no atoms once you average. And there are really 2 ways to compute it. You can take the expectation of this measure, or in this case and in many other cases, you can take finite boxes, okay, of this operator. Look at their eigenvalue distribution. Okay, so the eigenvalue, they draw the eigenvalues and do a histogram, and you take a limit as the box size goes to infinity. And that limit is deterministic, always, and it's equal to this expected spectral measure. Okay, so this is the lim of eigenvalue distributions.
Is it also atomic for higher dimensional distribution?
Yes, there's some exceptions, but typically yes. Now, there is an interesting thing that Dyson found. So, in 1952. So let's look at what is the spectral measure of Z. Well, if you don't put any randomness, then you can compute it using this way. Okay, so if you look at the finite box, then it's just a line. What does the eigenvalues of a discrete path look like? Well, it's just a sum of the left shift and the right shift. Those have eigenvalues that are evenly distributed on the circle, and then you add their conjugates. So what you take is you get a circle, a discrete circle of diameter of radius 2, and you just project it to the real line. Okay? That's what the discrete eigenvalues are, essentially. And then when you take a limit, you get a continuous circle that is projected to the real line, and that measure is called the arcsine distribution. Okay, it goes from -2 to 2. This is called arcsine. And there's some poles here, if you in the density near or not poles. There's some singularities of square root type near -2 and 2. But one thing is that everywhere else this is smooth, right? I mean, there's a formula for this that I'm not going to write down now. So what Dyson found is that this randomness manifests itself not just on the level of the spectral measure, which is that they become discrete, but already on the level of the average spectral measure. And the way that it manifests itself is the following. So this expected spectral measure of it with a certain kind of randomness. So he considered AI is distributed as the square root of an exponential random variable. You get the spike here in the middle. Okay, so it becomes, there is a big peak. Okay, and to say that precisely, let me tell you Dyson's theorem, and this is what we call Dyson's spike. Is the following. So if you look at the limit of mu of minus epsilon as epsilon goes to 0. So let me call mu is the expectation of sigma. Okay.
So what is the distribution of AI?
AI are the square root of an exponential random variable. So an exponential variable is the probability that, so it's positive, and the probability is that AI greater than x is e to the minus x. And AI is greater than 0. Greater than equal to 0. Okay, so that's what exponentials are. And in this particular case, this model is exactly solvable. So you can compute things precisely by various physics tricks. Actually, his paper is quite mathematical. It's a physics paper, but it's pretty much, a lot of it is quite rigorous. So when you look at this, and maybe I write it like this. So maybe if you look at this measure, so look at how much measure there is in this interval epsilon minus epsilon. If this was continuous, then you would expect something order epsilon, right? Some constant times epsilon. But what they showed is that this is asymptotic to, or this is, let's see, this is equal to, so there is a pi squared over 24 plus little 1, okay, divided by log epsilon squared. Okay, so as epsilon goes to 0. So you have to think of this as something extremely thick. Okay? There is a lot of stuff because log epsilon decays slowly. So there's a lot of stuff in this spike.
But this happens only for the square of the exponential distribution? Or
That's a good question. I think I have something to say about that. So this is Dyson's theorem, and this question was exactly asked by various physicists. This paper became kind of famous. So if you look in Google Scholar, there are 500 citations in the physics literature, and there are lots of follow-up papers. And in some of the physics follow-up papers, they have shown that this is general. Okay, but the proof there is all the proofs are very physicsy. They're complete, so I would call them maybe predictions. Okay, so the predictive thing is that they don't change. And in 89, so let me flip this. So Campanino and Perez in 89, they proved the following. So if AI is supported away from 0, boundedly, so that's in a bounded interval, and has continuous density, okay, then if you look at this thing, so mu of minus epsilon epsilon, then it's less than or equal to some constant over, if you look at the log epsilon, you have to take the third power. Okay, so for all small epsilon. So the mathematical result from 89, which was after all the physics results that were non-rigorous, was much weaker. So you get a worse power of log, and you get a serious restriction on the AI. Okay, and so our question was, is it true in general, and what is this pi squared over 24, for example? Like why is that here? So let me tell you the theorem that we proved, and this is with Marcin. So suppose that the variance of the log of AI, okay, log of the absolute value of AI, is finite, and let's call that sigma squared. Oh, it's not a good. Okay, let's call that. I don't know, S squared. So then we have the same conclusion as Dyson. So this the measure here is equal to, you have log epsilon squared and plus little o 1, and the constant here is simply sigma squared. Okay. S squared, sorry, too many sigmas. Okay, so first of all, you don't need to assume anything that actually has to be assumed, because this variance appears here in this answer. So if it's infinite, of course, this cannot hold. So under absolutely minimal assumptions, this can be a Bernoulli, so this can be coin tosses. As long as the variance of the log exists and it's finite, the same thing that Dyson claimed is true. And the pi squared over 24 just comes from the variance of the exponential distribution. So this is the first part, and in the next part I actually want to tell you not this motivation which comes from physics, but the motivation that we had to study this. This is completely different, interestingly. And then I'll give you some things about the proof. Okay, and I'll give you some generalizations. So the motivation that we had was the
Do you expect that there are other spikes?
No, we don't. And I will tell you, I will even tell you a little bit why. So I think towards the end I can give you some idea of why there is a spike. I can give you some idea why the variance comes in, and why there is log and why there is a square. Okay, and I can also tell you why you don't expect spikes elsewhere. So hopefully I can tell you all that. So our motivation was the following Luke and Lot conjecture, which is, let me see, it's written here, which is from 95, I think, Invenciones maybe, that was about something called the Novikov-Schubin invariant. So now we're back to groups, right? And I have defined you. So you have a Cayley graph for simplicity now. Okay, you have a Cayley graph of a group, and you understand what is the spectral measure of that is at a point, because I have defined to you. It's just the same thing. You take A to be the adjacency matrix. So the Novikov-Schubin invariant is just the limit of log of mu of minus epsilon epsilon minus mu at 0. So if there is an atom, you have to remove it, divided by the log of epsilon. Okay, so this is, let's see, am I doing this right? Yes, this is a log of that. And this is the limit as epsilon goes to 0. So what this is that this measure, mu of minus epsilon epsilon minus mu of 0, if this measure behaves like a power near, it has a spike that looks like a power near epsilon, then this spike should be like epsilon to the alpha. So if this is this Novikov-Schubin invariant is alpha, then this is how it's defined, and this is what it means, right? So this measure is roughly like epsilon to the alpha. Okay, so, and what this means is that this measure is singular. So for example, if you looked here in this, at this point of z instead of 0, so you could do that by shifting the spectrum by adding a constant, then you would get Novikov-Schubin invariant 1/2 there, okay, because there's a 1/2 singularity. And the conjecture of Luc and Lot was that this thing is always positive. Okay? So this is always positive.
Always meaning for any group?
For any group, yeah. Mm-hmm. And then as time went on, it was sort of reduced to, I don't know, finitely presented group, and then Lie groups, and I don't know. So I have a few things to say about that. Okay. So what I want to say about this first is that this is false, this conjecture, and that is the result of Łukasz Grabowski and myself. Okay, so let me write his name. So this is false. So there's a counterexample. And the counterexample essentially puts together two things. One of them is the Campanino-Perez result from 89. That is, you have this 1 over log decay, which actually corresponds in the spectral measure, in the expected spectral measure of a Schrödinger operator. So that's one thing. If you have 1 over log, then this is 0. Okay, just check. Yeah, because it goes much faster than. The smaller the alpha, the faster, the bigger the spike. So it puts together this, and it puts together a spectral equivalence. And the spectral equivalence is between, in the simplest form, is between Lamplighter groups and random Schrödinger operators. So what it says is that mu of some Lamplighter groups is equal to the expected sigma of some random Schrödinger operator. So that these two are actually exactly equal. There's no this is a precise thing. And so how many of you know about the Lamplighter group? Maybe you heard 100 times, so it's time for me to explain it again. Okay, so I should thank the organizers for providing me a perfect model of the Lamplighter group. So there is, in the Lamplighter group, there are lambs on Z. So you can imagine these boards to be the lambs. They're, a very nice model of Z2 squared, actually embedded in a S1 squared as a lattice. And then there is a Lamplighter who is me. And I walk around, and if I like, I flip this board, and if I don't, I don't. So every time I pass by a board, I flip it or not. So this is the Lamplighter group. Okay, and then there is more general Lamplighters, right? I mean, you don't have to put two-valued lights. You can have a general Cayley graph, a general group. They can take or they could even be a general graph. But if you want a group, you want a Rieth product, then you have to take some Cayley graph as lamps, and every time you pass, the way we do it is the lights are going to live on the edges. Okay, so here there are the lights, and every time you pass an edge, you make a move, make a random move in your corresponding light graph along the way. So the spectral equivalence is the following. So I told you what the Lamplighter is. It could be, by the way, the base graph also doesn't have to be Z. It could be any group. And this thing is true in that generality. So I told you what the Lamplighter group is, so you know what this object is. I just have to tell you what is the random Schrödinger operator. Okay, so what's the random Schrödinger operator? Well, you take the same base graph as you had in the Lamplighter, so in this case Z, and you have to put random variables on the edges. Okay, so what do you think will be the random variables on the edges? You have to pick some distribution, right? And this distribution has to depend on the Cayley graph of the lamp group, right? So what would it be? What would the distribution be? So clearly, what you put is that you put here random variables chosen from the spectral measure of the lamp groups. Okay. So if the spectral measure has an atom, as in the ordinary Lamplighter walk, because it has an atom at 0 and an atom at 1, I think, then our theorem won't work because you have. The log will not have variance. Yes?
I don't know about lamp group. So lamp group is a group where you label the vertices. So it's like a Rieth product.
So right, it's a Rieth product. Every edge has a label from the lamp group. And the way the random walk is, which correspond, or the way the Cayley graph is that the random walk is easier to explain. You walk around the base graph, and every time you pass an edge, then you will make a random step in the Cayley graph of the corresponding lamp group. And then it's easy to check this is a random walk on the Cayley graph of the corresponding Rieth product.
So why do you insist on saying edges? If you have a...
I don't. But for this talk, we will stick with edges. You can put the lamps on the vertices, and then none of this happens. So we don't have spikes.
If you have a general group as a base group, where are the lamps? On edges or on vertices?
So in the ordinary Rieth product, in a general group it will be on the vertices, but you can construct a group. Yeah, you can, for every group you can construct a Rieth product such that this model is correct, right? Even with the edges.
So you consider lamps on edges?
Yeah, I consider lamps on edges. Okay, so now you see, right? If you put together this spectral equivalence and the Campanino and Perez result, then you get right away that this thing is false. And this is what we did with Lukács. Now, of course, actually, I didn't tell you, because, so why did we, what is in the Campanino and Perez result, right? So you had to have a distribution which is supported away from 0 and had to have continuous density. Okay, so you can't do that with Lamplighters that are finite groups, because the spectral measure of that will be atomic. Well, finite groups of atomic spectral measures. So the only thing that you can use is infinite groups. So what we'd use is Z. Well, Z is not good enough because although it has a density, it's not continuous. It has a spike. Well, okay, we have to convolve it with itself, right? If you do it twice, okay, that's Z squared. It's still not continuous. It actually has jumps. But Z cubed will work. So we had to have a Rieth product with Z cubed, or Z and Z cubed, and then we could obey the conditions of the Campanino and Perez result. So finally, what we ended up. So then, of course, we wanted to understand what happens in the ordinary Lamplighter group with just two lamps, and we did. And the answer is that you do have these spikes. Okay. Now, not with the ordinary generators. Okay, because if you have the probability half switch and probability half not switch generators, then that has an atom at 0. So these AIs, so the log of it doesn't exist. Okay, the log of AI with positive probability, the log of 0 doesn't exist. So this theorem doesn't apply. But if the switch is a different probability than the non-switch, or you put some laziness or something, then you can. No. So what you have to do is Yeah, so the you have to do one of the things with a different probability, and then everything will work again. And you do have actually this spike, this counterexample, even in the ordinary Lamplighter group that everybody likes, just the simplest one in Z.
What if you remove 0 from the spectrum? Do you have something like a spike or itself in the spectrum?
I think we don't. So yes, I think so, yes. It's interesting, yeah. Okay. So finally, I want to tell you a little bit about the proof, but I want to conclude with another observation, which is that our theorem doesn't actually require these AIs to be independent. Okay, as long as they obey some kind of central limit theorem, because we actually will use central limit theorem, then you know these results can still be carried through. And what this is good for is that we can actually get something much simpler than the Lamplighter group to have this phenomenon. Namely, we have a lattice in the group Sol, okay, which is basically 2 by 2 matrices acting on R squared. Okay, so it's a semi-direct product. So there is a lattice in there which corresponds to an operator where the lights here are not actually independent, but they have strong enough mixing properties that there is CLT. And so our theorem is actually done so that it applies to this case. And therefore, we found a counterexample in the, which is a lattice in the Lie group. So it's really, you could say that, these Lamplighter groups are not really groups. But the lattices in Lie groups, you can't say that they're not groups. So it's really, this is really not. It's a very inspiring conjecture, but it's not true. I mean, a way to judge a conjecture is not whether it's true or not, but whether it does, leads to interesting research.
So you have a characterization when it is true?
So this is really interesting. You can have a lamps here on the vertices. So that corresponds to the same group, but a different Cayley graph. Okay, and the same group, different Cayley graph, you won't have this spike. So whether you have this or not is sensitive, extremely sensitive, just to change of generators. So it's there are examples, and you don't have a complete characterization.
In the case of salt, it is sensitive.
Yes, I'm pretty sure. Mm-hmm. Yes. If you put there, you can also put lights on the edges and
Is there a uniform control?
I don't know. I don't think so, but we'll see. And no, I think they proved this for nilpotent groups, no? So probably no. Okay, so this is it, and I want to tell you a little bit about the proof. How much time do I have?
10 minutes.
10 minutes, okay. So,
Actually, could you flip the board for a moment? Thank you. Who was that?
So, what do you want to see? Okay, good. So this is the matrix that we have, and we want to solve the eigenvalue equation for this matrix, right? So what does the eigenvalue equation look like? Well, first of all, we study the finite approximations. Okay, so we look at finite boxes and want to study the eigenvalue distribution of those guys. Okay, because that's the one way to understand the spectral measure. So we look at this finite box and we say, here is my matrix, right? If I multiply this with some vector phi, then you get lambda phi. Right? So notice that because of the structure of this thing, this is really a recursion for phi. Right? You start with something here, and then you can solve this line by line. And then lambda is an eigenvalue if the last equation is satisfied, because that's not automatic. But for every lambda, you can have everything satisfied except the last one. So but then when you do recursions, then really you can study that with products of matrices, right? So let me tell you what you have to do. So you write the matrix SK, okay, which is, I don't know if this helped, lambda over AK plus 1, minus ak over ak plus 1, 1 and 0. Okay, and you look at the following thing. So 0c for some c is equal to Sn. So this sk, it depends on lambda, right? And let's say this is length n plus 1. So there are NAs. S0 lambda applied to 1, 0. Okay, so here's a 2 by 2 matrix. And this is a random walk representation of the eigenvalue equation. Well, I'll tell you that why that is in a second. So just what I said implies that I start with this vector. I keep applying these matrices to it. And lambda is an eigenvalue if and only if you get some vector that looks like this. Okay, so the first coordinate is 0. So that's what this equation is. Now, you see that these AIs are random variables. So what you're doing here is you're multiplying random matrices. Okay, so it probably is, we like that, right? If they're almost independent. They're not quite because they're 2 in 1, but essentially they're independent. So this is a random walk. This is a random walk on the group of 2 by 2 matrices. I really love that. This is really want to study this kind of thing. But the problem with this random walk is that it's not just one random walk. It's lots of random walks that are coupled together, right? This lambda, for every lambda, there is a random walk. And the randomness is the same in them, and they depend on each other somehow. So there are actually 3 steps that go into the proof. One is to remove this dependence. Okay. The second is to understand this picture geometrically. Okay. And the third is to take a scaling limit. Okay. And so I'll tell you these 3 steps. So how do you do the dependence? It's actually quite simple. So the moral that you should take from this is that you take this process where you multiply random matrices, and this is what you have to understand. And they're dependent random matrices, but if you understand this process, you understand the eigenvalues. Okay? So the idea is to conjugate this product. So you look at S0 and you go all the way up to Sk and at lambda, and you conjugate it or you multiply it by this at 0. So you take Sk at 0 and S0 at 0. So if we were at near 0, and take the inverse. Okay, and let's call this Xk. Okay, so it turns out that when you study this process, it separates the randomness and the dependence on lambda. And I'll tell you how. Okay, so I tried, Okay. So what this is approximately is the following. Okay, so this is a product of matrices R, which are fixed matrices, 2 by 2 matrices. They depend on lambda, but only on lambda. And they're conjugated. Okay, so you start R lambda, and this is just R lambda, and then you take R lambda to the S. That's the S1, and then here you go all the way to Sk minus 1, S1. Okay, so what happens is that you have a fixed matrix, and this is at 0. Okay, so basically in the end you have to understand this process. Now what is this process? This process is actually something quite simple. And I'm going to now draw a geometry. Okay, so you have 2 by 2 matrices, so you expect a hyperbolic plane to come in, and it does. We'll think of it as the upper half plane. Okay, so if you think of these 2 by 2 matrices as automorphisms of the hyperbolic isometries of the hyperbolic plane in the upper half plane model. Okay, so here is R. Here is the upper half plane, and H. And what are these R's? So it turns out that these R's are rotations about the point I. Okay, and the amount of rotation is essentially lambda. It's maybe lambda over 2 or something like this. So if you want to, the way I look at lambda is by changing the amount of rotation. And what happens when you conjugate? These are conjugations, right? What happens when you conjugate the rotation? Well, you get a rotation around a different center. Okay, and how does the center evolve? Well, it evolves according to some products of matrices, right? So it's going to be a random walk. the center of this rotation is a random walk. And where is this random walk? Well, it actually turns out that at 0, these matrices, this thing disappears. So these are, just off-diagonal matrices. The product of 2 of them will be diagonal. So this random walk is extremely simple. You're just multiplying numbers. Okay? So in fact, it's an exponential random walk on the imaginary line. Okay? So you're just multiplying numbers, random numbers together. Okay? So you have an exponential random walk, and you move along, and you rotate things along the center. So this thing actually stays on the imaginary axis. So now I want to mention just 2 things. One is that the fact that this random walk is exponential that we are at 0 is very special, because the random walk stays in a subgroup, which is essentially the multiplicative group of R. So it behaves diffusively, okay? And that's the reason why you have this spike. If you look at everywhere else in the hyperbolic plane, you have a random walk on its automorphism group. It's going to have a positive speed. It's going to escape somewhere, and this doesn't. So it's going to behave completely differently, and that's why you don't have spikes there. And the second thing is that because it does a random walk here, it has Brownian scaling. So you expect a 1 and a 2 somewhere in the powers. So that's why you have a log, and that's why you have 2. And what happens when you do this? Well, basically, you take this process, you take the log of the whole picture. Okay, and you get this strip model of the hyperbolic plane. And this rotation has some point moving here up and down, and you have a Brownian motion here. Now it's an ordinary one, not a geometric one that moves around. And then you have to take a log, and then you have to take a further scaling limit here. And eventually what you get is some function of Brownian motion. So that's here. I think I just tell you, I'll skip a few steps here, because I'm really happy to tell you details, but I notice is if I tell you details here, then I get more happy and everybody gets more sad. So it's kind of involuntary transfer of power to me, and I don't like that. So what you get is actually that the number of eigenvalues in an interval, okay, can be described in terms of a single Brownian motion in the limit. And what it is you draw the Brownian motion and look at it, how many wells it has up to a fixed time, say 1, of a given depth. And that will be somehow the number of eigenvalues. And by taking limits the right way with n and epsilon, you can get the result that we want. But the point is that this sigma squared comes from the fact that you have a Brownian motion, and then what matters in these wells is really the variance of the Brownian motion. So I think I told you everything I wanted to. So just let you have questions.
Other questions?
Is there some non-physical interpretation? Is there some non-physical interpretation for the spike? Like, what does it mean?
Well, was this physical? I mean, in some sense, it means, right? It means you have this random walk, and then it behaves. So this is one explanation in one dimension. Now we have results like this now in higher dimensions, and it's harder to explain there.
That's not what I mean. Is there a physical phenomenon that
or non-physical interpretation?
Yeah, a non-physical interpretation that says what does it mean to have a spike in a physical system?
I think so. Yes.
And what the square root of the exponential distribution, when it has what does it become? What is special about the square?
Oh, it's just that with exponential things, very often models become just integrable, so you can actually solve things.
When you do it,
so you get what you get from that is the variance of the log of the exponential, and that's the thing that has pi squared over 24. It's equal to that. So that's the only thing that.
Translate it into this random walk in the hyperbolic plane.
So the Brownian motion. Okay, so you have a random walk whose increments are, you take the log of your variables and you take them with plus or minus signs. And essentially that's going to be the increments of your random walk in the hyperbolic plane. And that's the thing that goes through this Brownian motion. So in that case, these are the log of the exponentials times a half. Yes.
So if you have a more complicated element in the Q-frame to start with, can you still decouple the randomness and the coefficients?
No, yeah, this has nothing to do with probability. This is just group theory. Really. Yeah, it's an algebraic trick. Actually we invented this trick with Benedek Walko a while ago, and we named it Brownian carousel. It somehow comes into when you have beta ensembles of random matrices. It's a good trick to understand them that way. It turned out to be quite useful to be able to separate the randomness from the dependence on lambda.